Bismillah ar-Rahman ar-Rahim. Hello everyone. This is part 5. I will explain for you the fourth method, which is the series solution method. What are the steps? The first step, we let u of x, our solution, equal to the summation n from 0 to infinity a n x raised to n. We need to evaluate an, the coefficients. Okay, so we first substitute with the assumption in the Volterra integral equation. After that, we compare the right hand side and the left hand side according to the coefficients x raised to n, where n is greater than or equal to 0. Okay. After that, we will be able to evaluate an where n is greater than or equal to 0. You have now the values of an. You can substitute it in the assumption to get u of x equal to the summation and from 0 to infinity an. Now we know them, multiplied by x raised to n. We sometimes can be able to evaluate the nth term of u of x, and then we can get the closed form of the u of x. This is a nice explanation for the series solution method. Let's take a Volterra integral equation, u of x in its general form, of course, plus lambda, the integration from 0 to x, k of x and t, ut dt. We want to use the series solution method, so we will write u of x equal to summation n from 0 to infinity an xn. Okay, so we will substitute here and here to get summation an xn equal to of x plus lambda, the integration from 0 to xk sin t, summation an tn dt, n from 0 to infinity for both summations. Then we expand those summations. Okay, so a naught plus a1 x plus a2 squared plus and so on, and this will be equal to f of x plus lambda. We can get out summation n from 0 to infinity an because it's all constant, from 0 to x k of x and t raised to n dt. So after we integrate this, we can get something multiplied by x raised to 0 plus something multiplied by x, something multiplied by x squared, and so on. Let's say if this is a, this is B, this is C. So by comparing both sides, we get A naught equal A, A1 equal B, and so on. So we will rewrite u of x with the known values of the coefficients. So we get u of x equal to a plus bx plus cx squared, and so on. That's a very simple way to understand the series solution method. I hope you understand it. Here are the examples. As always, you solve the second group, I solve with you the first group. Let's do this. This is the first example that we need to solve it using series solution method. It's very easy as long as you know the summation form of the functions in the integral equation. And here we have sine x, and we know that t sine x, which is mean Taylor form of sine x, is equal to summation n from 0 to infinity minus 1 raised to n x raised to 2n plus 1 over 2n plus 1 factorial. Okay, so now we let u of x equal to summation an x n, where n from 0 to infinity. So when applying t on the integral equation, we put the summation for the xn. Okay, for 1 it's the same. For 2 sine x, we put 2 and then write the summation that we've mentioned. N from 0 to infinity minus 1 raised to n x 2n plus 1 over 2n plus 1 factorial minus the integration from 0 to x summation n from 0 to infinity a and t and dt. Okay, so here's tn because it's t here, and here is with respect to x. Okay, try to notice these things so you can reach to the right answer. Okay, now let's expand those summations. We have here a naught of x naught plus a1x plus a2x raised to 2 plus a3 raised to x raised to 3 plus and so on equal to 1 plus 2. We have here x over 1 factorial minus x raised to 3 over 3 factorial plus x raised to 5 over 5 factorial, and so on, minus Here we have to expand it and then integrate, or integrate then expand. So I choose to integrate then expand. So the solution of this integration is that we get the summation outside the integration of an. So we write the integration from 0 to x for only t and dt. Okay, so when we integrate Tn, we get what? We only get Tn plus 1 over n plus 1, okay? And never forget, of course, this constant part. So let's expand it. We have what? We have a naught t plus, put n equal 1, so we have a1 t squared over t over 2 plus a2 t raised to 3 over 3 and so on, and this is all from 0 to t. Okay, so from 0 to x, of course, we just need to replace each t with x. Okay, so let's replace each t with x. So here we will have x, here we have x squared, here we have x raised to 3. Okay, now let's compare the coefficients to get the values of an's, of the an, so we can write u of x with no unknowns. Okay, so at x raised to 0 we have in the left hand side only the a naught, so we write a naught equal to, and here we have only 1 because here is the smallest one raised to 1, and here the smallest one is raised to 1 too, so a naught will be equal to what? Equal to 1. Okay, x raised to 1, and the left hand side we have just a1, the right hand side we have 2 minus a naught. We know that a naught is equal to 1, so a1 is equal to 1. For x raised to 2, we have a2 equal to, let's see if there is x squared in the right hand side. Yes, there is. We have minus a1 over 2, so we write minus a1 over 2. a1 is 1, so minus 1 over 2. Let's get the coefficients of x raised to 3. We have a3 equal to, we have here x raised to 3 minus 2 over 3 factorial, which is 1 over 3, and also we have here so a3 will be minus 1 over 3 minus a2 over 3, and we have a2 equal to minus half, so we will write 1 over 6 minus 1 over 3, and this will give us what? If we multiply it here by 2 and 2, we will get minus 1 over 3 factorial. Okay, what about the coefficients of x raised to 4? A4 will be equal to, we will have it only in this part. Okay, so it will be what? It will be minus a3 over 4. a3 is equal to minus 1 over 3 factorial, so it will give us 1 over 4 factorial. Okay, let's do the substitution of these a's and the summation of u of x. We will have 1 plus 1 multiplied by x, which is x, minus half for x squared, and minus 1 over 3 factorial for x raised to 3, and for 1 over 4 factorial we have x raised to 4, and so on. If we take the coefficients of the even numbers and the coefficients of the x raised to even number and x raised to the terms which are even and the terms which are odd. So what we will get is 1 minus x squared over 2 plus x raised to 4 over 4 factorial, and so on, and this is added to x minus x raised to 3 over 3 factorial, and so on. And the first bracket is cosine x, and the second bracket is for sine x, and this is our answer. This is the second example, and we have to solve this first kind Fredholm integral equation. It's not Fredholm, it's for Volterra, because one of the limits of the integration is variable. Okay, and it's of the first kind because u of x is not outside the integral sign. It's just it is just inside the integral sign. Okay, what we need to know to solve it by series solution method, we have to know that t ln of 1 plus x is equal to summation n from 0 to infinity minus 1 raised to n x raised to n plus 1 over n plus 1. Okay, and in this method we let u of x equal to summation an xn, where n is from 0 to infinity, as I said before. So we rewrite the integral equation by the Taylor series, and we get minus x plus x squared over 2. Those two terms will not change. And then we write t ln 1 plus x, which is x plus minus x squared over 2 plus x raised to 3 over 3, and so on, plus x multiplied with this same bracket, which is x minus x squared over 2 plus x raised to 3 over 3, and so on. And this is equal to the integration from 0 to x to summation n from 0 to infinity an tn dt. And this is equal to, we can get an outside the integration because it is not depending on t, and t raised to n is the one that will remain. And this integration is equal to tn plus 1 over n plus 1 from 0 to x. And this will give us x raised to n plus 1 over n plus 1 minus 0. Okay? So we will write here x raised to n plus 1 over n plus 1. And this is of course equal to a naught plus a naught multiplied by x plus a1 x raised to 2 over 2 plus a2 x raised to 3 over 3 plus a4 a3 x raised to 4 over 4, and so on. Let's compare the coefficients of xn to get the values of an. So for x naught, or x raised to 0, we have 0 equal to 0 because there is no coefficients of x raised to 0, so it's as if there is 0 multiplied by 0 multiplied by x raised to 0 here, okay? And the other side, there is also nothing multiplied by x raised to 0, so 0, and the equation is right. X raised to 1. For x raised to 1, we have minus x, so minus 1. We write just the coefficients. And we have here x, so plus 1. And in the other side, we have a naught multiplied by x. And this is equal to a naught. So we have a naught equal to 0. For x2, we have half and minus half and 1. So we write this down, 1 over 2 minus half plus 1 equal to, the other side we have a1 over 2. So a1 over 2. This half will go with this half, and this 2 will come here, so we will get a1 equal to 2. For x raised to 3, we have this term, which is 1 over 3, and we have this term, which is minus half. Don't forget this x. Okay, so minus half, and in the other side we have a2 over 3. So we have what? a2 over 3. This part is equal to minus 1 over 6. This 3 will go to the other side, so multiply 3, and this will give us minus 1 over 2. So for a2 it is equal to minus half. For x raised to 4, we didn't write it, so let's imagine that there is term here. It will be according to this summation, and this will give us what? It will give us minus quarter. Okay, so minus quarter, and here we have this term, which is 1 over plus 1 over 3. This is equal to a3 over 4, right? So a3 over 4, and we will have here what? 1 over 12 multiplied by this 4, and this will give us 1 over 3. So a3 will be equal to 1 over 3, and this will give us that ux is equal to 0 multiplied x raised to 0 plus 2 multiplied by x plus minus 1 over 2 multiplied by x squared plus 1 over 3 multiplied by x raised to 3, and so on. So let's write this 2x as x plus x. Okay, so we'll get x plus, and we will get the summation of len 1 plus x, which is x minus x squared over 2 plus x raised to 3 over 3, and so on. So we can rewrite this as x plus len 1 plus x. Okay,